And the thing is that the old quantum mechanics was sort of limited to light having a dual nature with both wave and particle nature. But then it really sort of took off, and matter started to have waves. And um, when you write down equations for motion of things that are at the scale of quantum scales or small scales or microscopic scales or subatomic scales, these are all sort of synonyms of the same thing that I'm trying to say, small things, subatomic scales. Then turns out when you try to do the mechanics of that, which is to say maybe the position of that thing, little thing, say an electron, as a function of time, what happens is that you cannot really deterministically determine where this thing is. It is a probabilistic wave. It's given by a wave equation, and the wave equation actually gives you the probability of finding that thing, not the deterministic answer for finding that thing. Stuff like that. And uncertainty is an intrinsic part of this mechanics, and so we call this quantum mechanics, quantum physics, same thing. And it's led to, of course, also particle physics, and one of the contributors to that is Feynman. And we were kind of talking about the Feynman diagrams last night, where we basically established that, you know, even the wormholes and time travels can time travel as a topic can sound a little bit like sci-fi, science fiction, and it's very popular in science fiction, and it's very much written about. I mean, we've got people in the chat who's writing science fiction books, actually, like Steven. So it's very popular to think about wormholes and time travel, but it actually is quite real as well. It is allowed in physics to be able to do time travel. It's just not very pragmatic. It's just not very realistic to have those conditions be achieved technologically at this point. But we talked about the physics of it and how it is kind of possible, and especially it may just be very possible at the microscopic level. We talked about how particles and antiparticles are kind of actually already doing time travel. Okay, so maybe not a macroscopic level like you and I, bigger objects, maybe at the people like us and materials really like us. I mean the objects like us that have the scale of classical scales may not be able to do time travel very easily or at all. But microscopic levels, we might actually have time travel quite intrinsic in particle physics. And we even get Hawking radiation as part of that, because black holes actually emit stuff sometimes as part of quantum mechanics and quantum fluctuations. That's how they have temperatures. That's how they can do Hawking radiation, black hole radiation, black body radiation. But radiation generally means that you're emitting something, and if you're not emitting anything, which is classically thought of for black holes, because even light cannot escape a black hole from within its event horizon. But turns out in quantum mechanics, black holes can actually sometimes sort of emit things, which is how they get a temperature. So this mixing of quantum mechanics with classical physics in the case of black holes, to describe them more fully, is what Stephen Hawking is credited for. So if you want more detail on this, you should definitely go back in our live streams in the past and look up all the different black hole type of lives that we have done. So time travel, in other words, all of that is to say that time, can we get 10 likes, by the way? Hi, Completely Insane. Hello, how are you? Hi, Clint. Hello, Doro. Hello, Insane. Hello, Clint again. Are you the daughter of Einstein because you're smart like him? Oh, thank you. He did have a daughter, I believe. But I think he had mainly, I can't remember. I think he did have a daughter, actually. Watches tumbleweed roll by. Completely Insane. How do you know Reese? I thought you were new to the channel, but thank you so much for the 10 likes, by the way, guys. Can we get 20 likes? So you know Reese? Can you say hi to my friend Hugh Janus? Hi, Hugh. Acacio. Hello. Stephen, hello.